Hello, can you hear me?
Yes, sir.
Sir,
Yes, sir, we can
Good.
hear.
Yeah.
good evening,
Yes,
sir.
sir.
Good evening. So even the creep failure will not be there for the exam anyway, but because some of you have asked for creep failure, I am teaching. Okay?
Thank you, sir. Okay, sir.
Yeah.
So
All
thank
right.
you so much for this kindness.
Oh, no problem. You have to do well in whatever is done. Okay, until now. Okay.
Sure, sir.
Yeah. So
Sir,
the
the
last point,
exam syllabus will be
Failure theories and
from failure theories till
Fatigue.
fatigue.
only failure, static
From
failure
what?
theories, fatigue failure theories. That's all.
Okay.
Yeah.
Thank you, sir.
It's a 3-hour exam. All the
sir.
necessary formula, everything will be there in the sheet. You are not supposed to carry anything.
Right, sir. Right, sir. Thank you, sir. And sir, one request that, like, what I mean to say is the question difficulty should not be like that. We will not be able to solve it.
No, the question difficulty will be in such a way that if you
Yes,
have
sir.
an excellent preparation, you will be able to solve it.
Sure, sir.
If you have
Thank you.
not prepared for it, obviously you will not solve it.
Yeah, of course, sir. Like, you know,
Whatever,
sir, what I meant. Thank
no,
you.
whatever we have discussed in the assignments and the class, we are even for the quiz midsem also, I have asked the same thing.
Right,
I
sir.
have not asked something that is out of box. Okay.
Yeah.
Sure, sir.
So
Sure.
if you have prepared for that, you should be able to answer. That's all. Okay.
Yes, sir. Yes.
Sir,
Hmm.
only one clarification from your side, sir. Actually, we gone through now we are studying from the starting first lecture to till now. So, for assignment, how much weightage, sir, right now you consider?
We have already announced, no, assignment weightage.
Marks you have told me, sir.
How much?
15 marks. Sir.
Yeah, that's what it will be. Whatever percentage, that will be assignment weightage. I don't
Sir,
remember exactly right now.
Sir, now I will tell you, sir. 15 marks for assignment and 15 marks you have said something about the project, but there's no way we seen that things, but we are not able to do that project. So you can
Yeah.
consider as
So what we will do is we will change it 20 marks for assignment, 30 marks for midsem, whatever happened, and remaining 50
Okay.
marks for the end sem.
Thank you, sir.
Okay, sir. Okay.
Thank you, sir.
Thank
Thank you so much, sir. Thank you so much.
Okay.
you, sir. Thank you.
Okay, so shall we go ahead with the creep failure now?
Yes, sir.
Yes, sir. Yes,
Sure,
sir.
sir.
Yeah.
Sure.
So the concept of creep failure comes. Until now, we have talked about failure of these materials, but many times the issue is with the most of the times that we have discussed until now, we really did not talk about effect of temperature on these materials, particularly when the materials are operating at very high temperatures. So one needs to be worried about when the materials are operating at very high temperatures, the mechanism that is at play at such high temperatures are going to be very different from what you would see in room temperature behavior. So what are the typical issues at high temperature? We know plastic deformation is nothing but dislocation motion, isn't it? So because when we have the material is operating at high temperature, there is additional energy that is available to ease the dislocation motion. That means the material, the dislocations will move easily. So there will be an increased mobility of dislocation. That means it will be easy for plastic deformation to take place at high temperature. That is precisely the reason why you probably heard of this concept of forging, right? When you want to form into a specific shape, you heat it to a high temperature and then apply the stress, because it is easier to form at high temperature, because you can create plastic deformation easily. And similarly, we have talked about equilibrium concentration of vacancies. As you increase the temperature, number of vacancies will increase. That means the defects are increasing. And there are two ways that plastic deformation can happen. One is dislocation slip or dislocation climb, right? The climb will become more and more active at high temperature. That is why at high temperatures, your BCC and HCP materials also plastically deform easily. And usually you have the grain boundaries which will act as an impediment to dislocation motion. At these high temperatures, the grain boundaries being what you call the weaker spots, they are going to become more weaker, and hence the grain boundary, whatever resistance that it used to offer, will not be able to offer. So that means the grain boundaries themselves will deform. Right? So then also you will have recrystallization of grain growth in cold worker material. That means the grain start growing in size because of the temperature being larger, then hence you will have diffusion taking place easily over a larger distances, and hence grain size will increase. And the oxidation, because at high temperature, oxidation will be promoted much easily. So these are all detrimental effects that you don't want in materials when they are operating at high temperature. So that is the reason why you need to understand the behavior of these systems at high temperature. There are various engineering applications where this high temperature phenomena is very important. Steam turbines operate at close to 500 degrees Celsius and so on, and hence you need to be very careful with the design of the turbine components. Boilers, gas turbine engines, rocket engines, ballistic missile nose, which when they the noses usually subjected to very high temperature, re-entry vehicle noses, which are also subjected to very high temperature. So usually the high temperature strength. So when you measure the strength of a material, you should also normally when you mention this is the ultimate tensile strength of the material, we do not talk about temperature. Usually that is mentioned at room temperature. But when you increase the temperature and do the test, the ultimate tensile strength will be lower. It will be reduced. So the high temperature strength of materials is usually it is assessed with respect to a time scale. What do I mean by that? I will tell you in a couple of slides from now. And the tensile properties, if you measure at room temperature, they are independent of time, but high temperature strength will be function of time. That means at that particular strain, if you are operating at for a sufficiently long time, the load at which can withstand at that particular strain will come down. So that is very important. That is what we call relaxation of the material. And again, at high temperatures, the strength of the material depends on the strain rate and time of exposure. Right? The material strength depends on the rate at which you are loading more severely. And because they are dealing with metals, they exhibit normally at room temperature, they exhibit elastic property, but at high temperatures, several metals exhibit viscoelastic response, very similar to polymers. So, for example, if you have a tensile specimen, if it is subjected to a constant load at high temperature, then what happens? It will creep, meaning you take a specimen, you apply a load and hold that temperature at that, hold the specimen at that particular load. And this guy, if it is, this test is done at room temperature, the stress will remain constant. What do I mean by that? Suppose this is my stress and this is my time, and I am doing this test at temperature, room temperature, right? I have applied some strain. Because of strain, the stress has increased to that level, and then at that level of stress, strain, I have held the specimen. That means I have a tensile specimen subjected to constant load. Okay. So this is as a function of time, that is how I maintain the stress. Now, on the same plot, if I am plotting strain, let us say, then what happens? The strain will also increase some value. All right, at that particular time, it has gone up to that value. And then, if you are operating at room temperature, then strain also remains constant as a function of temperature. Time. As a function of time, the strain remains constant. This is my strain and that is my stress. Is that clear?
Yes, sir.
Yeah. Now, but if you are operating not at room temperature, let us say I am operating at a temperature T1, which is, let us say, greater than some, say, 0.5 times the melting temperature of the material. Then what happens is, at this point, the strain should have been constant, but because I am operating at very high temperature, the strain starts to increase. It will not remain constant. It will continue to increase. This is what we call creeping. That is what is the meaning of creep. Creep is nothing but the strain in the material as a function of time, although the stress is maintained constant. The material continue to deform. And that behavior is what we call creep behavior. Is that clear? What that is the meaning of creep? Creep is the deformation of a material when it is subjected to a constant load at high temperature. The material continues to deform as a function of time. As the time increases, the deformation increases or the strain increases. That behavior is what we call creep.
Sir, one small question. If you remove the load, then what happens? Will it come back?
I will talk about it. It will come back, but I will talk about it in a moment. Yeah. So I said when it is working at high temperature, this happens. At room temperature, the strain will not increase, but at high temperature, the system continues to deform. But what do you mean by high temperature? How do we define this high temperature? Is it 100 degrees Celsius, 200 degrees Celsius, 300 degrees Celsius? What is this temperature? Because a high temperature for one material may not be sufficiently high for another material. So how do we define this high temperature? So a particular temperature can be considered as high for one material, while for other material it is not. So a common measure is what we call a homologous temperature, TH. What is homologous temperature? Homologous temperature is the ratio of the test temperature to melting temperature. That means if you are operating it at T and the melting temperature is Tm, T by Tm is your homologous temperature. Creep in a material is significant to be worried about if your homologous temperature is greater than 0.5. That means if your operating temperature is at about 50% of the melting point of that particular material, that is when you need to be worried about creep deformation. Otherwise, you need not worry. So now we know the melting temperature of each material is different, and hence it is logical to say that to define this measure with respect to the melting temperature. So that is basically ratio of the working temperature to the melting temperature called homologous temperature. So if your homologous temperature is greater than 0.5, that means if your operating temperature is greater than 50% of the melting temperature of the material, that is when creep is significant. That is how the high temperature is defined. Okay. Now, okay, what kind of a test you need to do in order to see whether a material is good to be used under creep deformation or high temperature deformation? So the type of test that you want to use, the high temperature test for a given material, usually is determined by the time scale of its service for the said application. For example, if you are designing a component for a rocket engine, we know for sure rocket engines are subjected to very high temperatures. Yes or no?
Yes, sir.
But then, do I need to design the component for creep? Just because it is subjected to very high temperature, do I need to design it for creep?
Gas turbine
What is
engines,
creep?
So based on operating temperature only we have to decide.
Sorry, based on?
operating temperature. So
No,
it's
operating
supposed to.
temperature is going to be very close to your melting temperature. It is going to be more than 0.5 times the homologous temperature.
Not the rocket engine, but gas turbine engines do go
So
for thermal creep.
rocket engine need not be, because the amount of time that the rocket engine is operating at that high temperature is very short-lived. So that is why what kind of a test is required in order to decide whether this component is suited for creep application. It depends on the time scales of its service. Okay. For example, you can simply do a high temperature tension test. So you just need to do a tensile test at very high temperature to measure the ultimate strength of the material to see whether it is going to break or not. That reveals the performance of short-lived items such as rocket engines or missile cone nose, because they are not going to be working at such high temperatures at high loads for extended periods of time. They are only going to work for few seconds, if not minutes, right? In such scenarios, you just need to know what is the strength of this material at that particular temperature. However, for example, if you are dealing with a boiler, in the boiler you have a steam pipeline, right? And this steam pipeline is subjected to this high temperature for an extended period of time. Typically, you design these boiler pipes for 10,000 hours of life. Very long period of time. So that means it is subjected to this constant temperature and constant load for over such a long period of time. Then doing a simple high temperature tension test, because high temperature tension test will tell you what at that particular temperature, what is the strain. You are not waiting to see what is happening to the relaxation and all these things. So then that will not provide enough information. If you do a high temperature tension test in order to do a design of steam pipeline, that will not give you enough information because it does not talk about creep deformation. In such scenarios, you need to do creep test, because the creep test allows for the measurement of dimensional changes over a long period of time due to exposure to high temperature. So creep tests typically take very long times. So you just apply a dead load and keep it at some high temperature and wait to see whether the extension is happening in the material or not. And there is also another test called stress rupture test. What it does is it measures the long time load bearing response at high temperatures. So you wait for sufficiently long time and you will see whether the load capability to so here you will apply constant load. Here you will try to apply constant strain, and constant strain, whether you don't let the strain to change, but you let the stress to relax, test to reduce, so that you know at high temperature, if you are working for longer time, you may not be able to apply the same load at you are applying at room temperature. And there are also other aspects such as thermal shock and stress relaxation. They are also very important in high temperature application. So this is a very interesting graph that actually gives us some understanding of creep deformation, how we are going to do the test. So imagine you have a specimen which is subjected to a load sigma 1. At time t equal to 0, it is applied with certain load. And at that particular load, it is deformed instantly. There is an instantaneous deformation of epsilon 1 at time t equal to 0. Okay? And then you maintain that load there. You are not changing the load. And because you are at high temperature, what happens? The material is going to deform. So, and hence you will have the strain developed. This is an instantaneous elastic deformation the material is subjected to when you are applying the load. After that, you are maintaining the constant load, but because of the behavior called creep, there will be material deforming, right? Because there is thermal energy that is provided to the material, because of which there will be dislocation motion that is enabled because of the high temperature energy, the energy that is provided by the system, the high temperature to the dislocation motion. As a result, you will have a plastic deformation that causes this plastic deformation happening from epsilon 1 to epsilon 2. This is what we call inelastic deformation that happens between T0 to T1. If you have wait longer, and it would increase like that. Okay. Now let us say at time t1, t is equal to t1, you have removed the load suddenly. What happens when you have removed the load suddenly? Whatever is the initial elastic deformation, that will be recovered immediately, because elastic one should be recovered immediately. So from here to here, you will have epsilon 1 strain recovered. But then you have removed the load, but it will not come back to its zero configuration immediately. Immediately, the elastic one will be recovered, and because the load is removed, now there will be strain relaxation. That means the strain will slowly come to zero. Right? The strain goes to zero, and this is what we call elastic after effect. And this is typically what is observed in any creep deformation. And here we plot a curve called creep curve, which is very similar to your what we have studied crack length evolution. So
Paris
here,
law.
yeah.
Is it
Is
similar
there a
to
question?
Paris law?
Yes, you're right. Yeah. Similar to means looking like Paris law, but it is not Paris law. Okay. Yeah. So even in creep, you have three regimes. One is called primary creep, secondary creep, tertiary creep. Okay. So initially, when you have applied certain load, there will be instantaneous elastic deformation that is defined by epsilon naught. After that, as you wait for some time, there will be creep strain that is developing. If you look at this fellow in this region, if you take the slope of this line, it will be changing, right? Right? And then at point, this is after some time, you will enter something called a secondary creep regime, wherein strain rate remains constant. That means the creep rate, this is what we call creep rate. There will be a constant creep rate. Initially, there will be a creep rate initial be higher, and slowly it will reduce and it attains one value, and that value remains there for quite some time, and that is what we call secondary creep. After that, you will enter a regime wherein the creep rate starts increasing suddenly, and then eventually it will fracture. Okay. So this solid line that you have seen here is what we call idealized creep curve for constant load, and dashed line B is for constant stress. This is for constant load, and this is for constant stress. Because why these two are deviating? Because when the fracture is happening, the cross-sectional area will be changing, and hence load per unit area that will change. This is only load, and this is for constant stress. So that is why this line B is representing constant stress, wherein cross-sectional area is reducing. Now, the slope of this curve, d epsilon by dt, is what we call epsilon dot or creep rate. This test, as we have said, it is done at constant load. This primary creep, this is what we call transient creep, wherein the creep rate is evolving. And the secondary creep will be having a constant creep rate. This happens between what you call recovery and strain hardening. And this is also called steady state creep. That means the creep rate maintained constant. And the tertiary creep, because due to effective reduction in cross-sectional area, suddenly you will have void nucleation and then sudden failure that takes place after a long period of time. And people typically, this is called creep rupture strain, at which creep rupture happens, and the time for rupture. So this is very important to see how many hours can I operate a particular component at such high temperature. So one of the popular models for understanding creep failure is what we call Andrade's model. This is representing a constant stress creep curve, which is basically superposition of two separate creep processes, which is there is an instantaneous initial rise, that is epsilon naught, and then you have a transient creep, primary creep with decreasing time, and then you have a constant creep rate. which is called viscous creep. And all these things are embedded in this formula. This is what epsilon naught e power kappa t. So epsilon naught, this is your initial elastic one, and based on that you will define initial primary creep, that is all transient, and then you will have secondary creep. Okay, so beta and kappa are your material constants depending on the material. Similarly, there is also another model, Garofalo's model, which actually takes into account of steady state creep rate. That means the ratio of this guy also into the formulation. This explicitly, it will talk about total creep strain is instantaneous strain plus the transient creep limit, that basically this fellow, and then R is the ratio of transient creep rate to transient creep strain, and epsilon s dot is steady state creep rate. That is ratio of that. There, like you have different models for fatigue failure, you also have models for creep strain. And there is another test. Previously, we have done creep test. There is another test called stress rupture test. What does this stress rupture test do? It is similar to creep test, except that the test is conducted up to failure. You conduct the test up to failure and measure the stress at which the failure happens. Okay. So here what you do is you apply higher loads. As a result, the creep rates are also usually higher. The information that we obtain from this test is the time to cause failure at a given nominal stress for a constant temperature. You maintain at some it is a temperature T1, and if you are applying a particular constant stress, this is the time that it takes at time T1 for failure, and this is the time that it takes if you are operating at temperature T1 for failure at that particular stress value. So you are operating at constant stress and checking what is the time taken for the failure at a given temperature. So you can see at different temperatures, the slope is changing, and it is given temperature also, there may be change of slopes. And you can see that T1 is the highest temperature, T2 followed by T2 and T3. So the change in slope of these lines, they represent different mechanisms or structural changes of the materials because of different mechanisms that are at play, such as fracture at transgranular or intergranular fracture, oxidation, grains growing, and recrystallization. These are all different mechanisms that are at play, which causes the change in slope of these lines, or within a given temperature also there can be a mechanism change. You can see here there are two slopes. So the kind of structural changes during creep, they can happen because of the deformation by slip or subgrain formation and grain boundary sliding. These are all the, so you can have slip like what we have discussed in plastic deformation, and you can also have grains within grains, subgrains formation, and grain boundary sliding, because the grain boundaries become weak, the grain boundaries themselves might slide. That is also one form of plastic deformation. So this is how a typical creep testing machine look like. Very simple. A fulcrum based test, you will apply a constant load here, and this is your specimen, and you put a strain gauge to measure the strain here. For a constant load at a given temperature, you maintain this in a furnace so that the entire specimen is at constant temperature, and then you will have instantaneous elastic plus plastic strain depending upon the load that you apply, and then you will have primary primary creep, secondary creep, and tertiary creep, and then you will have rupture. In the stress rupture test, we are measuring what is the time that it takes at a given load for the rupture to take place. So these are data shown for lead. Lead being very soft material, at 17 degrees Celsius itself, it shows some creep behavior, right? These are all at a different stress value, loads are constant stress values, the strain versus time. So as you can see, with increase in stress, the creep strains also increases, right, for a given time. So this data is obtained for constant true stress instead of constant load by this guy Andrade's formula that we have used, it is obtained by this fellow Andrade. Okay, so data, so the key data to be reported after creep test is basically the stress sigma, temperature T, steady state creep stress, epsilon SC dot, and time of rupture. These are the typical properties that you need in order to put them in the appropriate formula. For example, if you are using Garofalo's model, you need to know what is your epsilon S dot that you will measure from the creep test. Okay. And you can also get different plots to represent creep data. You have true stress versus true strain rate, SC, that is SC dot is true strain rate at a given particular strain rate. That will be different for different temperatures. And here sigma versus time to rupture. You can also plot what is at a given stress and a temperature, what is the time to rupture. This is also another data. It's all one test, and you can represent several data, right? So in fatigue, you write stress versus stress life diagram. In creep, you write stress versus time to rupture diagram. So you can see here, this is typically how a creep data looks like. As a function of homologous temperature, you can see up to 0.5, the effect of creep will not be significant depending on what is the temperature, depending on the load that you are applying. And here you are seeing tensile stress versus homologous temperature, and you are seeing this is the region of creep, transgranular creep fracture, different mechanisms, intergranular creep fracture, and here it is rupture. So here at very long time, you will not have rupture happening, but you if you go to very high temperatures, then only the rupture happens, provided the load rating, strain rate 10 power 9 seconds is the time to fracture here. This is the time that it takes for fracture, so a very long time it takes. And if your homologous temperature is very low, then the rupture will not happen, but there may be a transgranular fracture that also happens at very high time scales. So this is typically what you would observe when you see a creep data. Okay, different fracture mechanisms. If you are having a typical ductile fracture, if you like a 0.2 is like room temperature, you will only see ductile fracture. You will not see this creep mechanism at all. The creep mechanism becomes more prominent below this line, and that is typically at a T by Tm close to 0.4 or something like that, right? So the creep data, you can plot stress versus the strain versus time for different sigma 1, sigma 2, sigma 3, and using that you can, the same data can be represented in different ways. That's all, right? So stress strain curve for various values of time, stress and strain for different time points are called isochronous strain curves. And using these isochronous strain curves, stress strain curves, we can measure the secant modulus, what is called slope at a given strain. For a given strain, you can measure a straight line, and then the slope of that line is what we call ES, and that can be plotted as a function of time, right? At a given time, the value of ES for different times will be given, and then you can plot the ES for that particular thing, and so on. The same data can be plotted in different ways to understand the mechanism, creep mechanism more detailed. And there is another data that people usually plot is the presentation of creep data, the steady state creep rate. What do you mean by steady state creep rate? This fellow, epsilon dot SC. That value as a function of 1 over T, the temperature at which you are operating, and that again will be provided for different stress values. This is at say 1.4 into 10 power 8 dyne per centimeter square. This is at 5.9 into 10 power 8 dyne per centimeter square. As you increase the stress, you can see steady state creep rate is increasing. And the slope of this line will give you something called activation energy. Steady state creep rate, or as a function of 1 over T, gives you a slope, and then you see that the slope of this line is constant, and the slope gives you activation energy Q. kilocalories per mole. And this activation energy tells you what is the amount of energy barrier that you need to cross in order to go from transient creep to steady state creep. So as we have discussed, the mechanisms, physical mechanisms that cause creep will be different for different materials. It will not be the same. So, and same, in some materials, it could be transgranular creep fracture. For some materials, it could be intergranular creep fracture. Intergranular means from one grain to another grain, there will be a fracture. Transgranular means within the grain, and so on. And of course, as we said, the value of stress and temperature will change the mechanism for a given material. And at high temperature, we know that the dislocations and everything move very fast. And you also have higher diffusion rates. Diffusion means the movement of atoms over a longer distances. So one of the most popular mechanisms of creep is what we call viscous creep. So it is like the viscous creep can be explained through the fluid flow problem. So the shear viscosity, the fluid flow problems, you can write tau is equal to mu times gamma dot, where gamma dot is the strain rate. So here the shear stress by shear strain rate gives you the shear viscosity of the liquid, right? So similarly, you can also define something called tensile viscosity for a material as eta is equal to sigma by epsilon dot, where sigma is the stress and epsilon dot is the strain rate, right? And then eta gives you the viscosity. That is what if a material, a solid material is creeping like a fluid, then this viscosity is what we call tensile viscosity, right? For an ideal viscous substance, which is incompressible, eta will become 3 times n tau. That means shear viscosity of the liquid. Now, the strain rate we are talking about can be represented in this Arrhenius form, where Q is your activation energy, which we have actually measured here for each material. And R is gas constant, T is the absolute temperature. So, and A again depends on the stress that you are applying. So the viscous creep can now be represented by, because we said A is a constant that depends on the stress. So now we can bring out that stress explicitly, and we can write epsilon dot is equal to A1, which is a material dependent constant times stress e power minus Q by RT, where Q and A1, these two are material constant. If they will change depending upon the mechanism that is at play. Okay, whatever the creep mechanism that is at play. So this is typically you will have different material A1 and Q for a given material. Depending upon the creep mechanism that is at play, these values will be different. And similarly, we have heard of creep in polymers. It may actually happen at room temperature for several polymeric materials. That is because their homologous temperature equivalent will be very close to room temperature. And hence, creep effects are usually applied. So when we talk about polymers, we define this high temperature, so-called high temperature, as glass transition temperature. So for most materials, the glass transition temperature will be as low as -100 to as high as 200 degrees Celsius. So that is why you can see the creep even at room temperature for several materials. Okay. For a crystalline polymer such as polyethylene, viscous flow occurs at temperatures just above Tg. That means their glass transition temperature. What happens when you have operated above Tg? The van der Waals, so the weak secondary bonds or van der Waals forces in the carbon-based molecular chains such as polyethylene, they become weaker above the glass transition temperature, and that causes the permanent deformation. Okay, so again, this process can also be described by a similar Arrhenius type equation. Epsilon dot is equal to A1 sigma e power minus Q by RT. That means epsilon dot represents the strain rate as a function of time. So again, the creep in polymers can be represented by this kind of a rheological model. We have a spring and a dashpot eta 1, which is this spring represents your elastic strain. This dashpot represents steady state creep, and the tertiary creep involves another elastic part as well as a dashpot. If you have to see that, if you are applying a constant load, this is the loading scenario. The strain will be, you have some elastic strain, and then you will have transitional strain. That means that is your primary creep and then secondary creep. This transitional creep TC is in here, and the secondary creep is primarily governed by this fellow, right? And then when you unload, only the elastic strain will be recovered, and there will be some time that is taken for transient creep to recover, and the secondary creep remains constant. So whatever, this will be the permanent deformation in the material. So we have in crystalline materials, like metals, you have three mechanisms like diffusional, flow, dislocation creep, grain boundary sliding, all these things. Depending upon whichever mechanism is at play, these constants will change. So the general equation for creep deformation in metals is given by this a little complicated equation. Instead of earlier you had only two constants, now A2, M, D, Q, and capital Q. These are all constants. You can, I don't expect you to remember this formula, but understand that it is also similar to, imagine this guy being this A2D power Q by T is another constant A1, for instance. Okay, so sigma is your stress, D is your grain size, because the creep deformation depends also on the grain size, because if your grain size is smaller, there are more number of grain boundaries, and hence grain boundary sliding is more active, and hence the grain size also comes into picture. A2, M, Q and capital Q, they are all material dependent and particular creep mechanism at play. What do you mean by particular creep mechanism? Whether it is a diffusional flow or dislocation creep or grain boundary slide. So the temperature influence is very similar to viscous creep formulation, because it is e power minus Q by RT by 1 by T. This is very similar to, the temperature effect is very similar to viscous creep, but otherwise it depends on the size of the grains and so on. So as I said, there are three mechanisms. One is the diffusional flow. This can take place at low stresses but very high temperatures, because when you have high temperature, the diffusion can take place. That means the atomic motion can happen over long distances, which will create vacancies in a material. Okay, so they will create a spontaneous vacancy formation near grain boundaries, and even at a lower stress, that will cause some deformation. Okay, there is so the diffusional creep is also represented by something called Nabarro-Herring creep. In literature, they call Nabarro-Herring creep, because Nabarro is a material scientist from South Africa. He contributed significantly to understanding of plastic deformation of materials, and hence his name is given. So here, this equation is after this equation represents the Nabarro-Herring creep, where the vacancies move through the crystal lattice. And if the strain rate is the strain rate in this case is proportional to strain, M is equal to 1, and inversely proportional to the square of the average diameter. That means in the Nabarro-Herring creep, M is equal to 1, Q is equal to 2. And there is another creep mechanism called Coble creep mechanism, where M is equal to 1, Q equal to 3. Depending upon the material, you can, I'm not going to go into the details when Nabarro-Herring creep is more dominant or Coble creep is more dominant. But if at all, when you know that the mechanism is more described by Coble creep than Nabarro-Herring creep, then you have to take Q is equal to 3. Okay. And again, the activation energy Q is very similar to activation energy for vacancy formation in materials in the crystal lattice, or QB for diffusion along the grain boundaries. The other one is dislocation creep. It is also called power law creep. So this is what happens is at a very high temperature, you will have a drastic motion of dislocations because of the additional energy that is provided by the high temperature. So this can happen at very high stresses, but at intermediate temperature, where diffusional flow is small. So when diffusion is very less, but dislocation creep can take place if your load is very high, even though temperatures are small. So dislocation climbing. So if your dislocation is on one slip plane, if it goes from this slip plane to this slip plane, this is what is called climb. If the dislocation is moving on the same slip plane, that is called glide. If it is moving from one slip plane to another slip plane, that is what is called climb. So this climb is more energetically strenuous. That means it requires more energy. And this can actually take place during this mechanism called dislocation creep. Okay. In this particular scenario, the grain boundaries do not play any role, and hence Q will become is equal to 0 and M value will be from 3 to 8. Because there it depends on the stress. That is why it is not necessarily proportional to stress, but stress to the power 3 or 4 or whatever. So in summary, you have depending upon the mechanism, if it is a diffusional creep, M is equal to 1, Q equal to 2. Is Coble creep, M equal to 1, Q equal to 3. In grain boundary sailing, it is 2 and 3. If it is dislocation creep, this will not be, Q will not be playing any role, but M will have a large range of values 3 to 8. Okay. And the activation energy for creep, as we said, Q is your activation energy. If you take logarithm on both sides, then log base 10 on both sides, then you will see 0.434 Q by R 1 over T base E. This is not T, log base E. So if you take from this, you can see that the activation energy Q will be same for all stresses, irrespective of, there is no stress dependence. And hence, if you plot log epsilon dot versus 1 over T, you will see parallel lines. That is why steady state creep. So this gives you parallel lines, right? 1 over T versus steady state creep. That is what rate. That is what we are seeing here. We are plotting as a creep rate, and then different you will have parallel lines for different stresses with different intercepts. So if you do epsilon dot for this equation, if you take this equation, if you plot log epsilon dot T versus 1 over T, that will produce straight lines all having same slope proportional to Q. So that is how you can actually compute activation energy depending upon your creep law. If you take this creep law, that's simply epsilon log epsilon dot versus 1 over T will give you Q. If you take this creep law, log epsilon dot T versus 1 over T will give you an integration of Q. Okay. So you can see that the activation energy has increased the temperature, the activation energy increases. Afterwards, it remains constant. So activation energy, this is the activation energy for pure aluminum, activation energy for creep for pure aluminum as a function of temperature. Again, as I shown you earlier, you have pure plastic deformation if the homologous temperature is less than 0.4%, 0.4, only plasticity takes place. As your homologous temperature increases, then you can see depending upon the stress value that you are operating or strain rate that you are operating, different mechanisms that take place. This is a power law creep domain. This is diffusional flow, and there's nothing here. Okay. I think, yeah, this is same mechanism. So if you take a nickel specimen with a deformation mechanism map as shown in this figure, if it is subjected to a stress of 6 MPa, okay, at a temperature of 900 degrees Celsius. 900 degrees Celsius, meaning you need to know what is the melting temperature of nickel. Let us say it is the, according to 900 degrees Celsius, let us say the homologous temperature is about 0.6 and it is subjected to a stress of 6 MPa. So you need to compute what is the corresponding this is the normalized shear stress and this is shear stress at room temperature. So you can measure the shear stress at 6 MPa. Corresponding to that, you can look at the homologous temperature and that will be your shear strain rate. The strain rate at which, so for example, if you are at 0.6, let us say this is your stress and then you can see that will be the strain rate and you can see this is high temperature creep, this is low temperature creep regime, this is the diffusional flow. You will be able to compute what is your strain rate for that particular scenario. Yeah. So now, how do you estimate life? The time temperature parameters and life estimates. Suppose if you have a creep problem, creep deformation eventually leads to what? Rupture in the material. That means the breakage or breaking of the material. In typically in metals such as crystalline materials like as metals, you may have voids. So here you can see voids generation appear along the grain boundaries. The small voids appear along the grain boundaries and precipitates. And this is what we call cavitation. That might eventually lead to the failure of the entire component. And when these voids coalesce and form a larger crack, and that is what we call final fracture or creep rupture. So in ductile materials at a very high temperature, you will have other mechanisms called dynamic recrystallization, because there will be diffusion of the material at very high temperature. Then there will be recrystallization of the material, and you will have large deformation without rupture because of the voids getting repaired and so on. So, but however, in engineering applications, if you are operating a component for about say 10, 20 years, you don't want excessive deformation, right? So, and hence you need to know what is the time for which I can operate this guy at such high temperatures. So, it is very difficult for us to generate data for such long periods of time. Let us say you want to identify what happens after 20 years. You cannot do experiment for 20 years. So, usually creep test data is available mostly for 1000 hours. So if you look at this fellow, this is a true stress and steady state creep strain at a temperature of 482 degrees Celsius. And this data is usually available for 1000 hours or at most sometimes 10,000 hours, and very rare occasions up to 100,000 hours. 100,000 hours is about 11 years. Most of the creep data is available for 42 days. One creep experiment will minimum take 42 days. So now if you have to estimate the behavior at low strain rates and a longer time for a service temperature of interest, what you would do is you will typically extrapolate these lines and find out what is the true strain rate, critical secondary creep strain rate, right? So now this stress life plot, one can obtain by extrapolating the calculated the rupture life. However, please keep in mind, extrapolation is always dangerous, right? Because the slope is not expected to remain constant. The slope may increase suddenly or remain reduced suddenly. If it is maintaining constant, it's not a problem. If suddenly increases, then the stress at which you think it is failing is not going to be that. So suppose, let us say, here it is like that and suddenly the slope reduces, then you will have trouble. And hence when you are the creep data, there will be a lot of uncertainty like fatigue data. So in order to avoid this extrapolation, what people have suggested is there are some better approaches. You have to use the data from relatively short time tests, but at temperatures much above the service temperature. So you are accounting for, instead of, if your room operation temperature is 100 degrees Celsius, you will still operate at a lower, shorter period of time, but higher temperature. Okay. So why do we do that? Because the physical mechanism for test and service are more likely to be similar when you are operating at high temperature. So here we will use the two parameters for life computation, that is called Shelby-Dawn parameter and Larson-Miller parameter for time temperature approach. So here you say this is the creep strain as a function of T e power, this is time e power minus 36,000 by RT, and this is time T is in hours. Okay. So you have this epsilon dot A times sigma e power minus Q by RT. Here the only assumption that we have is the activation energy is independent of anything. It is constant. If you take activation energy to be constant, you can write d epsilon is equal to A sigma e power minus Q by RT dt. Right? Because by integrating this, you can do that. And then steady state creep rate, if you integrate that, and then you will get theta is equal to T e power minus Q by RT. And this is what we call temperature compensated time. And that is what we are plotting on the x-axis. So for a given epsilon SC versus theta plot, you will get a unique curve for each material. You can see this is a unique curve for 98% aluminum. This is a unique curve for a different aluminum. This is a unique curve for a particular aluminum alloy. And you can calculate the creep strain at rupture. When the creep strain corresponding to rupture can be, it will be more or less constant for a given temperature composite at time theta r. That is this fellow. So the theta r now depends only on stress. So for a single material, you should have a single curve relating theta r and stress. So you now define them something called SD parameter. What is SD? Sherby-Dorn parameter. TSD logarithm of theta r, that is given by log TR minus 0.217 Q by T. So now if you would plot log TR over 1 over T, then this is y, let us say this is y and 1 over T is your x. So M is 0.217 Q, that is a slope. And if you extrapolate that line, that will give you the log TR, that is what you call rupture time. You can compute the rupture time. That is how you can calculate the life that is available for a component. Okay, so here you have an engineering component made of certain material subjected to in service to a static stress of 200 MPa at a temperature of 600 degrees Celsius. What creep rupture life in days is expected? So this is for the same alloy, the creep rupture PSD curve. This is Sherby-Dorn parameter curve for 200 MPa is given as at 200 MPa load at 200 MPa. This value is minus 16. Sherby-Dorn parameter is minus 16. So PSD is equal to log TR minus 0.217 Q by T. That is given as minus 16. And then if you solve this equation, you get the rupture time as 134,277 hours. That means this guy can be operated at that particular temperature at a static stress of this value for 5,595 days. Okay. Similarly, Sherby-Dorn, there is also another parameter called LM Larsen-Miller. This is also very similar model, but a little different than the other fellow. And it should not, you can follow this. I'm not going to discuss this, but it will give you, if you go through the slides, it should be able to make it clear for you how it is calculated. Okay. Again, you can compute the life that is for the same material. If you are operating at 200 MPa at 600 degrees Celsius, again S590 alloy, at you see that it is 9,052 days. So different models will give you different values, as we know already from other failure theories. So which one should I use? SD parameter should I use or LM parameter should I use? It depends on the type of scenario or the loading scenario that you have. Based on that, you should use one of the two, right? I think, yeah. So now, if you would plot stress versus rupture, you can now define two what you call safety factors: safety factor in stress and safety factor in time. Exactly similar to what you would do in the case of fatigue failure, right? That I don't have to define what is N sigma and NT. Okay, so one important aspect that I want to stress upon here, all the time when we have talked about creep, we said the material is at constant temperature and constant load. And this temperature is above the homologous temperature. That is when this creep deformation and all these things happen. But now imagine what would happen at that higher homologous temperature, at a temperature higher than the homologous temperature. We have maintained the load constant. But now what if you are cycling the stress also at a non-zero mean stress? Then you have creep plus fatigue. That makes the life much more complicated, right? So the creep fatigue is possibly one of the most complex things one can study, and till date we don't understand how because they are all non-linear processes. It is very difficult to develop models that can actually explain or predict the failure with reasonable accuracy when both creep and fatigue, both of them are present. Okay. I think with that I'll stop. We will not, I think this is possibly because there is nothing else to cover. So this is the last class of this course, and I wish you all the best for the final exam. Okay.
Thank you, sir.
Unless,
Thank you, sir.
unless if you have any other questions, I'll close the session.
Sir, only thing that whatever we require some practice some, sir. If you
I
have
will
it-
give you, as I told you, I will give you the assignment on fatigue failure most likely by tomorrow. I was on it, but I somehow forgot to upload it. By tomorrow, I will upload it. Yeah.
Right, sir. Right, sir.
Yeah. Any other questions?
Sir, for this creep, what kind of reinforcements you can make? Like you will change the material or what? Like what
You
are
have to do some alloying, which will reduce. See, what we said at high temperature, the problem is there will be dislocation motion,
yes.
right? So you should add some alloying or some impediments to avoid the dislocation motion. So you need to improve you need to increase the homologous temperature of the material by adding an alloying element,
Got it, sir. Got it.
right?
Thank you.
Yeah. Any other questions?
Yeah, Professor. For final exam, like the portion, most of the portion which is covered after midterm will be prioritized, or how is it?
The
Like,
final exam, you will have static failure theories, fatigue failure theories. That's all.
okay, sure.
Yeah.
Thank you.
Okay. So I see that in quiz midterm, some people have not been able to perform well, but please make sure that you will be able to refresh your fundamentals and be able to write the exam well, the final exam. Okay. I hope you have learned something about failure in this class. Okay. Let's see how it spans out in the exam.